So in this lecture, we are going to discuss about the Pfaffian differential equation. A Pfaffian differential equation is a differential equation. It is actually a differential equation of the form. So a differential equation of the form capital F1 x1 x2 up to xn dx1 plus capital F x1 x2 up to xn dx2 plus so on capital F x1 x2 up to xn dxn equal to 0. So the equation of this form, it is known as Pfaffian differential equation. And in this lecture, we are discussing how to solve this Pfaffian differential equation, where this Fi's, that means F1, F2, Fn up to Fn, they are continuous functions of x1, x2 up to xn, where this Fi's I running from 1 to n are continuous function. And the expression which we have on this side, that means if I call it the equation number 1, so the expression on the left hand side of equation 1, it is called Pfaffian differential form. So the expression F1 dx1 F2 dx2 up to Fn dxn. Now I'm not writing this F1 is a function of x1 x2 up to xn, so you should understand the expression, this, it's called Pfaffian differential equation. So Pfaffian differential form. Now the definition of this Pfaffian differential form, it should be exact. So definition of exact. A Pfaffian differential form is said to be exact if we can find continuously differentiable function mu not mu but u x1 x2 up to xn such that du equal to, if we can write down, that is f1 dx1 f2 dx2 up to xn dxn. Okay, then the such equation is known as exact differential equation, or I can say it is exact form. For example, if I can consider uh, yz dx plus xz dy plus xy dz equal to 0. If this is the differential equation is there. So this expression, or I can say this is a Pfaffian differential equation in the terms or in the variable xyz. And this expression I may write as d of xyz equal to 0, because you just see that in the first, so this d stands for a derivative, kind of differential, a differential of x, this is differential of y, and this is differential of z. So here first two variables are constant, differential of x, then second two are constant, differential of y, then third and then differential of z. So it is kind of this. So here u function is this xyz, and this f1 is this yz, f2 is xz, f3 is xy. So this form is, so I can say that dy dx plus xz dy plus xy dz is exact. So that is the definition of exact and the example of exact. The next definition is integrable. Okay, when we can say a Pfaffian differential equation is integrable. A Pfaffian differential equation is said to be integrable if there exists a non-zero differentiable function mu of x1, x2 up to xn, such that the Pfaffian differential form that is mu into f1 dx1 f2 dx2. So after multiplying this mu to this expression f3 dx f fn dxn is exact. So the previously the Pfaffian, whatever the Pfaffian differential equation is given, it is not exact. But if you are able to find out some mu, if you multiply to that, then that Pfaffian differential equation is known as integrable, and this mu is known as integrating factor. The function mu is known as integrating factor. And this u of x1 x2 up to xn equal to constant, where c is constant, it's called the corresponding, or is called the integral of the corresponding Pfaffian differential equation. Okay, and we know that, or we can say that a differential equation is said to be exact if the Pfaffian differential form is exact, and the surface u of x1 x2 up to xn is equal to constant. It is a surface in Rn, and so what is actually we have some notes here. The first one is a Pfaffian differential equation one. It's called exact if the Pfaffian differential form which is f1 dx1, f2 dx2 up to fn dxn is exact. The second note, that observe that u of x1 x2 up to xn is equal to constant. If this is a constant quantity, is a surface in Rn such that every point on it, the normal has direction ratio that is f1 f2 up to fn, because dx1 dx2 up to dxn is actually, it is in the direction of a tangent, and we have a direction of this two, that is dot product of this two will be have 0 here. That means f1 into dx1 f2 into dx2 up to fn into dxn is 0. So the dot product of this two is 0. That means this f1 f2 up to fn, it is in the direction of a normal, because this quantity, that is dx1 dx2 dxn, is a direction into the tangent, and perpendicular to tangent we have a normal. So that is the things we got. Now we have one result which is regarding the Pfaffian differential equation of two variables, which you are actually dealing with the same kind of equation in your F5 BSc class. Maybe in the graduation you have solved certain examples, that is of the type m xy dx plus n xy dy. So this is also a Pfaffian equation. Okay, and you have already did this type of things over there, And there also you are talking about integrating factor, finding the integrating factor and all sort of things. But here this theorem tells you that any Pfaffian differential equation in two variable, there always exists integrating factor. So it says that there always exists an integrating factor for the Pfaffian differential equation in two variable. So if you have a differential equation in two variable, then in two variable like this is always has integrating factor. That means you can able to integrate that. That means you can able to find out the solution for that. So what is the proof for this? Let us consider a two variable Pfaffian equation, that is p of xy dx plus q of xy dy equal to 0. Let us consider this. If you consider this q of xy is non-zero, then we can write down dy by dx from this. We can write dy by dx is equal to p of xy upon q of xy with negative sign. And this is what? This is the first order PD, sorry, ODE. And we have seen the existence theorem in our previous course, that is ordinary differential equation. In the unit 4, we have an existence theorem of a solution of ordinary differential equation, first order ordinary. So this is a first order ordinary differential equation. So from the existence of existence theorem for first order ODE, ODE means ordinary differential equation. The above equation has a solution. Let's say that solution is f of xy equal to c1. Then if you differentiate this with respect to, or I'll say it is by gradient of this one. So it is del f by del x into dx plus del f by del y into dy. So it is things which we are talking in this fashion, that is f, which is a function of two variable x and y. Let us take this x is a variable function of t and y is also function of t. So if you want to find out a derivative of f with respect to, you should write del f upon del x into dx upon dt plus del f upon del y into dy by dt. So this is actually df by dt. So if you want to write down this differential f, so you should not write this one. So exactly the same expression we have here. That is equal to 0 due to the c, derivative of c is 0. And this is exact from differs from this p dx plus q dy by the factor, as we have the same solution, and this factor is nothing but the integrating factor. Okay, So we say that this exact Pfaffian form differs p dx plus q dy equal to 0 by a factor as they have same solution. And this factor is nothing but the integrating factor. And this completes the proof of this theorem. In general, the Pfaffian differential equation in more than two variable, it may or may not be integrable. Okay, in the next theorem that we are discussing is we shall derive a necessary and sufficient condition for the integrability of the Pfaffian differential equation in three variables. And for that, I need to have some lemmas which is required to prove. So we shall first prove this two lemma and we go further for that. So first lemma that we need to discuss is let u of xy and v of xy be two functions of x and y such that del v by del y is non-zero. If further del uv by del xy is also 0, then that means this Jacobian is 0, then there exists a relation that is capital F of uv equal to 0 between u and v not involving x and y respectively. So this is the theorem, or I can say a lemma. U and v are the two functions which in the variable xy, such that we are taking this function with this condition. That means this Jacobian is 0 and this del v by del y is non-zero. Then there exists a relation f of uv equal to 0 between this u and v we have. That is the objective, is to prove. So to prove this, since given that del v by del y is non-zero, we can eliminate u is equal to u of xy and v is equal to v of xy and obtain, we eliminate y. We eliminate y between these two and we obtain the relation that is capital F of uvx equal to 0. We will now show that this f is also does not depends on x, and that leads to this expression f of uv equal to 0. Okay, so our objective is to prove that this f function is independent of u and v. Sorry, it is independent of x and y. So due to this, del v by del y is non-zero. We have done that. Now we will show that f does not depend on x. Now on differentiating this equation, let's say this is star. Differentiating equation star with respect to x and y, we get. So what we'll get? So here f is a function of three variables, u, v, and x. In particular, u is also function of xy, v is also function of xy. So we have the situation is this: f is a function of three variables, u, v, and x, and this are the function of x and y. So del f by del x, if you go via this path, there is no go further, so it is del f by del x plus del u by del x, sorry, del f by del u into del u by del x. So if I go along with this part, and then if I go along with this part, that is plus del f by del v into del v by del x equal to 0. And if you differentiate with respect to y, we have only two things. So that's why it is del f by del u into del u by del y plus del f by del v into del v by del y equal to 0. Now we have to eliminate del f by del u from this two expression. Okay, so what we'll do, there are many ways to do this. Either you can find out the value of del f by del v from this, and you can substitute here. And this can be possible due to this del v by del x is non-zero, since it is given. Okay, so it is given that del v by del y is non-zero. So from what we'll do is, this expression, the last one, will give you del f upon del v is equal to minus of del f upon del u into del u by del y upon del v by del y. From this we have this, and we substitute this value of del f upon del v here. So that will eliminate del f upon del v from this. So if I can call this as equation 1 and this is equation 2. So putting value of del f upon del v from 2 in 1, we get. So first del f upon del x is already there, plus the second term, that is del f upon del u into del u by del x. So that is also there, del f upon del u into del u by del x plus you have this del f upon del v. Del f upon del v is this minus of del f upon del u into del u by del v y upon del v by del y into del u by del v by del x equal to 0. That is we have here. If I take the LCM as del v by del y, so that's why this will give me del f upon del x into del v by del y plus del f upon del u, that I can take common, and what is the quantity is left here, it will left is del u by del x into del v by del y, because this I have taken as LCM, then minus due to this minus sign del u by del y into del v by del x equal to 0. And what is this expression? That expression is actually del uv upon del xy. That's why this will be del f upon del x into del v by del y plus del f upon del u into del uv upon del xy. That is a Jacobian of uv with respect to xy equal to 0. Now this one leads to, due to this, the what is given situation is this quantity is 0. That is our hypothesis that we have taken. That is del uv upon del xy is 0. So that will gives you del f upon del x into del v by del x is 0. So this quantity is left equal to 0 because del uv upon del xy is 0. Now since del v by del y is non-zero here, del v by del y is non-zero, del f upon del x is 0. Because the number a, b is equal to 0, it implies that a is 0 or b is 0. And here del v by del y is non-zero. So that's why del f upon del x has to be 0. If del f upon del x is 0, then what we can say is f is independent of x. Okay, and that's the objective we can go get. That is our objective. So hence f is independent of x. What we have did here, we have proved that this f is independent of x as well as y. That means f is only function of uv equal to 0. And that was the objective of this lemma. There is another lemma before doing or proof for 3 variable, integrability for 3 variable. We'll have, that is another lemma is there. Now, if x bar is equal to PQR, where P, Q and R are the functions of x, y, z, and if this x bar into curl of x bar. Now, what do you mean by curl? You should know that is 0. Mu is arbitrary function. arbitrary differentiable function of x and y and z, then mu into curl of x into, sorry, mu into x bar into curl of mu into x bar is also 0. So what is this theorem or this lemma is tells you, if x bar is a sum function of, or it is a vector of 3 variable, and if x bar into curl of x bar is 0, and if you multiply that x with a mu, where mu is any differentiable function, then mu into x bar and dot curl into mu into x bar is also 0. This dot is nothing but the dot product between two vectors. Okay, so let us first of all see what is the curl of x bar. First of all, those who don't know what is the meaning of curl of, here x bar is p of p q r is there. Curl of x bar will be I j k. Okay, that is del by del x, del by del y, del by del z, p q r. This is my curl of x bar. So as per the, if you expand this determinant, this will gives me del r by del y minus del q by del z. That is doing the cross product of these two. I minus sign for this, that is del r by del x minus del p by del z, j, plus del q by del x minus del p by del y. So in the middle it is del r by del x. Yeah. So this is the things we have into k. That is the curl. So what is x bar into curl of x bar? The x bar is pqr. So dot product of this one with pqr. So it is p into del r by del y minus del q by del z plus, so if I can write down plus with this plus, r into, due to this minus I just write down this p first and then r last. So it is del p by del z minus del r by del x plus q, sorry, not here, it is not r but it is q, and it is r into del q by del x minus del p by del y. This is the things we got. And they have given that this is equal to 0. That is our hypothesis. X into curl of x is 0. And we are writing this is in the short form. That is, we are writing as a summation of p into del r by del y minus del q by del z, where this summation is over x, y, z. So what we have do the rotation when we change this sum. P will change to Q, Q will change to R, and R will change to P. Whenever you have P in the next term, that will change to Q. And wherever you have R, that will change to P. So you can have the second expression. Third expression also will be there. And in same manner, the x will change to y will change to z, and z will change to x. In this way, it rotation. The meaning of this summation is this. What I am explaining. Why? Because we are lazy and we don't want to write whole expression. These three terms. Instead of that, we just write one term and we will work with this. Okay. Now, what is the things we have? We have mu into x bar. We have to prove that mu into x bar into curl of mu into x bar is 0. That is our objective. What is x bar? Here x bar is PQR. So mu into x bar is mu into P, mu into Q, and mu into R. So if, see what is the changes we have? Whenever P is there, we have mu into P. That is the change we made. So if I have found that x bar into curl of x bar is this expression, then what will be the mu x bar into curl of mu x bar will be? So just P will change to mu P, Q will change to mu Q, and R will change to mu R. That is the expression we have. So that's why this is summation xyz mu P into del mu by del R by del Y minus del mu Q by del Z we have. So this summation means there are three terms. Now, to do this one, we have to differentiate this inside bracket terms, because there is no problem with the first one. Here you have to apply the product rule, because mu is also a function of x, y, z, and it is differentiable function. So that summation will be summation of x, y, z, x comma y comma z. Mu p is already there in bracket. Mu as it is a derivative of r with respect to y plus r as it is a derivative of mu with respect to y. Then for this one also we have the same thing, minus mu as it is del q by del z minus q as it is del mu by del z we have. Now you just combine these two terms, that means this one and this one, that will write separately. This is mu into p is multiplied to that both term. So we have in the first summation mu into summation xyz p into r p into r into del v by del mu by del r del y minus q into del mu by del z. In the second summation, mu is independent and p is also there, that is summation xyz p. Now what is the expression is left? This one I have included here, so this one is left, and here is also, and here it is also mu is common, so that's why it is mu square. You have del r by del y minus del q by del z. Now this mu is as it is. Let us expand this sum. Let us expand this sum. So what we have here, we expand this sum, what we have, what is the situation? We have to move p to r, sorry, p to q, q to r, and x to y, y to z, and z to x. So if I expand this summation, the first one is PR del mu by del y minus PQ del mu by del z. That is the first bracket. Plus second bracket. That means wherever Q is there, sorry, P is there, we have to replace Q. So it is Q R, so it is P. Del mu by Y, so it is Z. Minus P, so it is Q. Q, so it is R. Del mu by del X, because it is del Z. Z is replaced by X. Plus, now here Q was replaced, so that instead of that we have R now. R, then P is replaced by Q, so RQ. Del mu by del Z is replaced by X. Minus Q is replaced by R. R will replace by P. Del mu by del X will replace by Y. This is my first summation. That is the first one. What is the second summation? The second summation is actually mu square into x bar into curl of x bar. That is exactly the x bar dot curl of x bar is there. That you can check. X bar into curl of x bar is summation of P del R by del Y minus del Q by del Z. That is exactly the same. And what is the situation we have? You just observe that this will be get cancelled out. The last term is cancelled. Del Q del R, so that two terms will cancel. PQ, this two terms is cancelled. So this will be 0. X into curl of x bar is already given as 0. So finally you will have mu into 0 plus mu square into 0. So you have 0 answer. So that is our objective, was to prove. Is the converse of this result is true? Can you make the converse of this? What was this result? X into curl of x bar is 0. Then mu into x bar dot curl of x bar, mu into x bar is 0. Is the converse is true? Converse is true if mu is non-zero. Okay. So the converse is also true. So we should write a note here, and it is easy. It is actually easy to see. If mu into x bar dot curl of mu into x bar is 0, then obviously you can common out mu from here and you can common mu here. Here if you common mu, then it is mu square will be common out. Then it is x bar dot curl of x bar is 0 if mu is non-zero. Okay, so that is the things we should write here. Now the main theorem that we are talking about. That means the theorem is a necessary and the sufficient condition that the Pfaffian differential equation is integrable. Okay, this is very important. This theorem is says that a necessary and sufficient condition that the Pfaffian differential equation that is x bar dot d r bar. The x bar is PQR and d r bar is dx, dy, dz. A dot product of this two. That will gives me p. P is a function of x, y, z. So p dx plus q dy plus r dz equal to 0. So Pfaffian differential equation in 3 variable. The integrable if x bar dot curl of x bar is 0. So it will say that x bar dot curl of x bar is 0. What is x bar? Is PQR. If it is 0, then we can say that the given differential equation is integrable. That means we can able to find out the solution for that. Okay. So the proof, let us discuss the proof for that. The proof is slightly lengthy, but we'll do this. So here the question is a necessary and sufficient condition. So first we'll talk about the necessary condition and then we'll talk about the sufficient condition. Okay, so we first so that the condition is necessary. That means we have to prove that if this equation is exact, then x into curl of x bar is 0. Okay, so if the equation p dx plus q dy plus r dz equal to 0 is integrable, then there exists integrating factor. Then there exists differentiable function mu of xyz and u of xyz such that du equal to mu into p dx plus q dy plus r dz, where mu is non-zero. Mu is actually a function of xyz which is non-zero. However, what is du? As per the differential, that means u is a function of 3 variables: x, y and z. So it is del u by del x into dx plus del u by del y into dy and del u by del z into dz. So if you compare this to equation now, if I can say this is equation 1 and this is equation 2. Comparing this equation 1 and 2, what we will have? Del u by del x is mu p, del u by del y is mu q, and del u by del z is mu r. So comparing equation 1 and 2, we get mu p equal to del u by del x, mu q equal to del u by del y, and mu into r is equal to del u by del z. That means what is mu into x bar? Mu into x bar is mu into PQR. That is mu P into mu Q into mu R. But what is mu P is del U by del X, del U by del Y, and del U by del Z. What is this? This is actually a gradient of U. This is what? This is nothing but a gradient of U. And the gradient may be defined or denoted as this gradient of U. And we know already this relation since the curl of gradient of U is 0. Due to this, what is gradient of U? We have obtained that it is mu x bar. We'll say that mu x bar is 0. And if the curl is 0 vector, therefore, or hence, mu into x bar into curl of mu into x bar is 0, because this vector is 0. So dot product of 0 vector with any vector will be 0. This is 0 scalar and this is a vector. And in the previous lemma, what we have proved is mu into x bar, curl of x bar is 0, or I can say converse of the previous lemma, which implies that x bar into curl of x bar is 0. So that proves that if the differential Pfaffian differential equation in three variable e dx plus q dy plus r dz is 0, if it is integrable, then this is the condition. So we have proved the necessity of the condition. Now the converse, that is sufficient. So now we shall prove that the condition is sufficient. So we shall prove that this condition is sufficient. So suppose that Z is treated as a constant, then the differential equation P dx plus Q dy plus R dz becomes, so what I have taken is Z is a constant, treated as a constant. So that means this dz will become 0. So that means this equation will become P dx plus Q dy equal to 0. Since this Pfaffian is in two variable, now this is a Pfaffian equation in two variable, and we have already discussed that the Pfaffian in two variable always has a solution. That is the lemma 1 we have discussed in this lecture. Okay. So since a Pfaffian differential equation in two variable is always integrable, this has a solution of the form. So it may have a solution of the form u of xyz equal to some constants C1, where C1 is a constant, but here we have treated Z as a constant, so this C1 might be a function of, it is maybe a function of C. Sorry, it may be a function of Z. So it may involve Z. In addition, there must exist a non-zero differential equation mu. So in addition, there exists a non-zero differential function mu such that del u by del x is equal to mu p and del u by del y is equal to mu q. Why? Because that is the solution of this one. Now, if you substitute this value del u by del x mu q into the equation 1, or now I'll start with this. Now p dx plus q dy plus r dz is there. So we multiply with mu here. So mu p dx plus mu q dy plus mu r dz is there. But what is mu p? We got the value of mu p is del u by del x. So therefore it is del u by del x into dx plus del u by del y into dy plus del u by del z into dz. So this mu r is not there. This value is not there. But I am adding this value, and here I am subtracting this del u by del z into dz equal to 0. So ultimately we have this expression. Now what will this implies? This will implies that this, what is this quantity? This quantity is nothing but the du plus, I may call this as capital K dz equal to 0, where this capital K function is mu r minus del u by del z. Okay, now what is given? Given that x bar into curl of x bar is 0. So by the previous lemma, this will implies that mu of x bar into curl of mu of x bar is also 0. Now you just observe this. What is mu into x bar? Mu into x bar is mu p, mu q, mu r. But mu p we have obtained it here, that is mu p is del u by del x, mu q is del u by del y. So we'll substitute that value. This is del u by del x, del u by del y. And what is mu r? Mu r we can get from this equation, that is we have here. A mu r is k plus del u by del z. So it is del u by del z plus k. We separate this two. that is del u by del x, del u by del y, del u by del z plus 0, 0k. What is this? The first is gradient of u plus it is 0, 0k. That is your mu into x bar. Hence, mu into x bar into curl of mu into x bar, we have already given 0. If I substitute this value here, then this mu into x bar is this. That is del u by del x, comma del u by del y, comma del u by del z plus k. Dot product with. Now what is curl of mu x bar? Curl of mu x bar. Let us calculate that first, and then we will come to this. So curl of mu x bar is ijk del by del x, del by del y, del by del z. The mu is this del u by del x, del u by del y, del u by del z plus k. So this is, I should write a straight line. Because it is a determinant. So you will have three vector here. Sorry, three component here. Del u by del x with respect to this. So that will mean gives you del u by del x del z plus del k by del x minus del u by del square u by del x del y. Second, what is our second component? That is minus of. So I'll write this one first. Del square u by so what I did wrong, huh? That is del square y. Here it is y. Here is also y. In the second one, you will have del square x del z plus k minus del square u by del z del x. But it is of minus, so this is also minus and this is plus. And the third quantity we have, it is del square u by del x del y minus del square u by del x del y. So finally, what is left quantity is this will get cancelled out. Here is also we have y. So this is del k by del y. This will be minus, this is del k by del x minus del k by del x, and this quantity is 0. So we substitute this value here. So I'll start again. So here we should not write this. Now we can write here. And here I'll start with this. Now we have mu into x bar into curl of mu into x bar is 0. We have given. That will implies mu into x bar is del u by del x, del u by del y, del u by del z plus k. And this value we have calculated this del k by del y minus del k by del x is 0 equal to 0 we have. So if you do the dot product of this two, will gives you del u by del x into del k by del z minus del u by del y into del k by del x and equal to 0, because 0 into this will be 0. What will be this quantity? This is actually a Jacobian of, so del uk by del xy equal to 0. And we get this. So hence a k can be expressed. So as we have used the previous result, one of the lemma in which we are talking about pq, if they are the function of u and b, we are function of, is if the Jacobian is 0 with respect to x and y, and del k by del y is non-zero, then we can able to express some function which is independent of x and y. So hence what we can say, hence k can be expressed as a function of u and z alone, as the equation 1 suggests us. Not 1, whatever the number we have. I think so number is 3. This is my equation number 3. And it is indicate that a relation between u and k independent of x and y, but not necessary of z. Therefore, the equation, that is del u by del, this equation, if I call it as double star, so the equation double star can be written as del u by del, sorry, not del but du by dz, but now u is only function of z, plus k u z equal to 0. What was that equation? Just see that. That equation was du plus k dz equal to 0, where k is this function. What we have achieved is this k is independent, and u and k are the functions which are independent of x and y, but they may be a function of z. So u is a function of z, so I can just divide this equation double star with the dz. So that's why this k is a function of u plus it is z. And now this is in the expression which we got, it is an first order differential equation. And we know that the first order differential equation, by existence of the theorem, will always have a solution. So that possesses a solution. Let's say that solution is phi of u z equal to some constant, where that c is some arbitrary constant. And this is the solution now expressed in the form of u of xyz. By using the capital U is in terms of xyz, and therefore we achieve our Pfaffian equation is integrable. So this is what? This is the first order differential equation. So it possesses a solution. Let's say phi of uz is the solution for that, is equal to some constant, where c is a constant. Now by using the expression, now this is the solution. So this solution can now express in form of u of xyz equal to c by using the expression of capital U in terms of x, y, and z. And therefore, since this equation has a solution, therefore our original equation, that means therefore the Pfaffian equation differential equation p dx plus q dy plus r dz equal to 0 is integrable. And that completes the proof of this result. Still, there are examples are left for based on this theorem and what we have discussed for Pfaffian differential equation. Okay. So if you have any question, you can ask.